So we'll get to something where we can make use of some of the building blocks that we have built so far, so that it removes boredom for one thing, and it actually shows that all these building blocks are actually worth something. You can put them together and make something which is remotely useful. Other than, of course, the sheer intellectual pleasure of seeing fourth order polynomials factored and poles and zeros and all that, right? Actually see that all that stuff actually makes sense, and you can make something useful. And the first candidate that we look at is what is called the bandgap voltage reference. The bandgap it just turns out to come from some physical from physics of the device, but the basic idea, the necessity for this is that we are always in a big mixed signal system trying to interface from the real world to the digital world. The digital world understands only ones and zeros, and therefore every number in a digital state machine is dimensionless, whereas real world signals are all analog and have dimensions. So clearly, to go from a dimensioned world to a dimensionless world, you have to divide by some quantity which has the same dimensions, right? So if we consider all our signals to be voltage, then to be able to get a dimensionless representation of that voltage, you have to divide by some number, some quantity which also has dimensions of voltage. And clearly, it makes sense to divide by some quantity which remains stable over whether the process changes. I mean, finally the real world signal is something, right? You want to represent it in digital form, okay? So you divide by some quantity which does not change even if the supply voltage to your chip changes, correct? So whether your battery voltage is 3 volts, 3.5 volts or 4 volts or 1 volt, you want the digital representation of the natural signal coming in to remain unchanged. That's a reasonable thing to expect, right? Okay? The next thing, of course, is that it shouldn't change with ambient temperature. And you might wonder, what is the big deal, right? Because in Chennai the temperature always seems to be 40 degrees. So what is the big deal? Okay? So well, even in Chennai, you have some cold spells, and you would say generally the temperature remains between maybe 25 and maybe 45 or so, all in centigrade. All right, but there are cold countries in the world where the temperature can go as low as minus 40, right? And at that point, it really doesn't matter whether you're talking about centigrade or Fahrenheit. Minus 40 centigrade, minus 40 Fahrenheit is the same thing. And on the other extreme, you will have temperatures soaring up to 50 Celsius, which, so therefore, this is the ambient temperature. But you know that all chips produce heat. So even though the ambient temperature is only, say, can vary from, say, minus 20 degrees centigrade to perhaps, say, 50 degrees centigrade, the actual junction temperature, which is what the device cares about, doesn't care what is there outside, right? What matters to the device is its junction temperature. The temperature of the transistors inside the chip, can you guess whether they'll be higher than the ambient or lower than the ambient? They'll be higher than the ambient because the chips are producing heat, right? And that heat can be removed only at a finite rate because of finite thermal conductivity of all packages and so on. So the junction temperature of the transistors is somewhat higher. So while the ambient temperature is something, this ambient temperature first of all can have a big range, and not only that, there is also junction temperature which is could be a few degrees above ambient. So basically the transistors in the chip are subject to wide excursions in temperature. That's the bottom line. And that's for civilian applications. In military applications, of course, you are subjecting missiles and all this other stuff to very, very large excursions in temperature, because your missile could leave off here and get into the ionosphere and then go and hit somebody somewhere, right? And you want to make sure that it hits the right person. Okay, so you better make sure that all the signal processing you do is reasonably accurate. So temperature excursions are easy to combine. That's the bottom. And you basically want the quantity by which you divide you're taking this natural signal and dividing it by a voltage reference. That reference better be invariant with respect to pretty much everything under the sun, right? Within limits, of course. But if your battery voltage changes from 4.3 volts to 2.7 volts, you still want this reference to remain what it was without moving. Right? Similarly, if the temperature changes from minus 25 degrees to or minus 40 degrees to 125 degrees, you still want this voltage reference to remain put at the same value. It should be an absolute invariant with respect to process changes, temperature changes, as well as supply changes. That's the requirement. Okay. So let's start off with what do you think the first thing you will attack is? You want such a kind of reference. So the voltage reference should be invariant with A, temperature, B, process, C, power supply voltage. Okay. All right. So where do you think you will start attacking the problem? This is what you want. I mean, can you think of any voltage where you've already to be able to we already know that the VBE of a forward biased transistor is about 0.65 volts or so. The first thing I would say is, hey, this seems like a constant voltage, why don't you just use this? So what would I do? Then what is the next experiment I would do in the lab? Yes, Sudhir, Prasad, Komala. Do you understand? It's like a common sense thing to do. So if you plot the VBE of a transistor with absolute temperature, forward bias junction, I must say, PN junction. Right? It turns out that this VBE, as I promised, is roughly about 0.65 volts, but has got a temperature coefficient which is negative. Okay? And the slope, does somebody know? Is basically minus 2 millivolts per degree centigrade. Right? This happens to be like this, that's all. To get into further details of why it is minus 2 volts per degree, millivolts per degree centigrade, you have to go and sit, get into the device physics and then figure out why. But without knowing any of the physics as a practical engineer, what I would do is we take this diode and then sweep temperature by putting the thing in an oven and plot VBE as a function of temperature, and then it turns out that I get a thing like this. But I want something which doesn't vary with temperature, right? So what should I do? What do you think I can do? Have something where the voltage is decreasing with temperature. If I want something which is independent of temperature, what should I do? So the straightforward way of doing this is to add something which increases with temperature, right? So I will right. So if I add I will call that VP tat. Okay, I'll justify the reason a little later on. But if I add a voltage to this VBE, where the temperature coefficient of the quantity I add is precisely 2 millivolts per degree centigrade, but positive, then when I add these two voltages, I should get something where the dependence on temperature is lost, right? So you basically end up with, in principle, with voltage which is independent of temperature. Okay, so VBE plus VP temp. This is the basic idea, right? And again, as you see, there is no rocket science. It seems pretty straightforward, common sense. Okay. Now the question is, how do you get something where, how do you get a voltage where this voltage you want it to exhibit a positive temperature coefficient, and the temperature coefficient must be plus 2 millivolts per degree centigrade. Okay. And again, the answer to that again is not too difficult to see, right? So you know that if I have a diode, the VBE is what? What is VBE as a function of I? VT ln of I by IS. Okay, as long as I is much larger than IS, which is, very reasonable assumption. Okay, now if I took, say, a diode, or if I put n diodes in parallel, and pumped I, what is VBE? So VBE1 is this, VBN is? How do you figure this out? There are n diodes in parallel, so each diode must be carrying I by n. So this voltage must be VT ln I by IS by n, which is Ni by IS. I'm sorry, VT by I by NIS. Okay? So what can you say about VBE1 minus VBEN? It is VT ln n. And what is VT itself? Raja Rao? KT by Q. Right? So in other words, if I operate two diodes with different currents, then the difference between their voltages, forward bias drops, is of the form KT by Q ln n. And can you comment on the temperature dependence of this? It is not only does it increase with temperature, it increases linearly with temperature. Okay? And in fact, this is directly proportional to the absolute temperature. Correct? Okay. Now, so now we have two characters. One, which is simply VBE, whose temperature coefficient is minus 2 millivolts per degree centigrade, and we have this VT ln n, whose temperature coefficient is what? K by Q ln n, right, which is VT by T ln n. Correct? And what is this now? At room temperature, VT is 25.8 millivolts, okay, by 300 Kelvin times ln n. Okay? This is the temperature coefficient of the difference between the forward bias voltages of two diodes, where the ratios of the areas of the diodes is n. Does it make sense? Okay. Now, what should I do? I have something which decreases with temperature, I have something which increases with temperature. So what should I do? If I simply connect them, does it automatically? I need to adjust the positive temperature coefficient such that it is exactly equal to 2 millivolts per degree centigrade. Okay? In other words, I got to multiply this Vt ln n, okay, with some number k such that this plus Vbe has 0 temperature coefficient. Pardon? No. Vt ln n is the voltage, right? That I have to multiply with some number k and add to Vbe, right? This has got a positive temperature coefficient, this has got a negative temperature coefficient, right? And to find the number k, what will I do? The temperature coefficient of this is nothing but Vt by T ln n times k and this must be equal to 2 millivolts per centigrade. Okay? So what does this tell you? Which means that this ln n times k must be equal to 2 millivolts times 300 Kelvin divided by 25.8 millivolts. K. How much is this? Can somebody calculate and tell me? It is very rough calculation. Is if I assume that it's 25 millivolts, then it is 12 times. Yeah, it's about 24 should be the number. What is it actually? It is 23.2. Right? So in other words, I have to add, in English it means that I have to generate 23.25 times Vt and add it to Vbe, and I will, if I do this, then I will get a voltage which is independent of temperature, right? And what is 23.25 times Vt? This is the Vp tat that I was talking about. This is exactly 600 millivolts, right? So this is 600 millivolts and this is approximately again 650 depending on the construction of the diode, either 600, 650 or so, right? So if I add this to this, the constant voltage I get, which will be independent of temperature, will be how much? 1.25 volts. Okay? And if you so this temperature invariant reference that you get by adding to VBE a quantity which depends directly on absolute temperature. So that positive temperature coefficient voltage that you are adding to VBE, please note, is a multiple of Vt. Vt is directly proportional to absolute temperature. So this component is often called the Ptat component, where Ptat stands for proportional to absolute temperature. Okay? That will be about 600 millivolts, and you can add, if you add that to VB, which is about 650 millivolts, you can expect this constant voltage to be about 1.25 volts.
So how will you get K to be invariant of temperature?
Okay, so the question is, this is all a very nice story, but how can you get K to be invariant with temperature? K is the amount by which you must gain up this Vt ln n. Okay?
You solve up a negative feedback.
Please note that K is dimensionless. So, it must be dependent on ratios of two like components. Correct? Which means that if temperature changes, both the components, if you choose them properly, both the components change by the same amount, so the ratio K remains constant. Does that make sense? So, making K invariant with temperature is definitely not a problem. The next thing, of course, is that making ln n temperature invariant is also not a problem, right? Because if you have one diode and you have 9 diodes, for example, in the n, I mean, clearly as temperature changes, the 9 diodes remain 9 diodes. When it gets hot, doesn't mean that you'll get 18 diodes suddenly, correct? So making ln n independent of temperature is also a straightforward thing. So it seems as if there is no catch here, right? Okay? And in fact, it seems almost too good to be true, alright? And okay, so the thing is that when reference that you would expect to get, okay, and this can be traced to the silicon band gap. So this voltage is often, this reference voltage generator is called the band gap voltage reference, and this is a standard fixture in almost all analog ICs you see today, for the reasons I just mentioned. Okay, and this is the theory, right? So the next thing is, the circuit designer is to, we verbalize what we want to do. What all do we want to do? The first job is to find VBE. That's straightforward enough. Pass some current into a diode, you will get VBE, right? Okay. Then the next job is to generate VT ln n, right? And that's also straightforward enough. Take two identical currents, which we know how to do. Push them into one of the currents into one diode, the other one into n diodes. Okay. And the difference between those two voltages is known to be Ptat, right? And you need to gain that up by some factor K, where we have to make sure that this K times ln n is about 23 point whatever, 2 or something. So as a circuit designer, your job is to A, generate VBE, to generate VPTAT, 3, add VBE to VPTAT, and to generate the final output voltage, which is often called VBG. In schematics now you will see VBG, that means V band gap. Okay, so this is the basic idea, and of course you have infinite ways of doing all these three tasks. Okay, all right. So let's see, and you could also argue that, hey, why should I add VBE to VPTAT? I will add VBE by 10 to VPTAT by 10, correct? And I will get VBG by 10. That's perfectly fine, right? There also will end up with a voltage which is invariant with temperature. It will be a fraction of this 1.25 volts, or you can have a multiple of 1.25 volts, whatever. But the basic idea is, to VBE you must add about 24 VT to get something where it doesn't change with temperature. Correct? So the first, this seems straightforward enough. There's pretty much nothing to do. Correct? This seems like a little more involved thing, right? Not because you have to have one diode and n diodes, but because you have to amplify the difference. So you take this voltage Vt ln n and amplify it up by some gain K. Alright? Okay. So the first thing is, of course, the choice of n. So clearly, it makes sense to start worrying about how am I going to generate this B PTAT. Once I generate PTAT and generate VB, what all ways can you think of adding them up together? I mean, if I had this voltage and that voltage, simplistically, adding voltages, putting them in series. Two voltages in series, right? That's one way. Another way is to convert each of them into a current and then add those two currents, join those two currents, and then pass it to a resistor. That's another way of adding. So you can see that in spite of my balding head, there are still a million ways of doing the addition. So then it follows therefore that if there are m ways of doing A and n ways of doing B, and there are p ways of doing the third thing, there are clearly n times m times p circuit diagrams possible for a band gap. And so you will find a variety of circuit diagrams out in the literature. I'm obviously not going to discuss every one of them, right? So I'll discuss some stuff which is commonly used. Okay. So the first thing is to take this PTAT voltage, which is, what is V PTAT? It's nothing but it's of the form VA minus VB, where VA is the voltage drop VB of one diode, right? VB is so this is the VB of one diode. This is the VB of n diodes. Okay, but what is the key point that we are missing here? Both these must be, of course all the diodes must be identical, but the sum of the currents through the n diodes must be exactly the same as the current through one diode. So both of them operating at the same current. Correct? And we want to multiply this by K. Alright? So, so if you think back a little bit, to achieve gain, one way of doing it is to convert VA, we want VA minus VB by R. So let's try and figure out how to generate VA by R. Okay? So you want to convert VA to a current. Okay? And push this current into a large resistor. Right? And so if you are converting voltage to a current, that basically means that this current must be of the form VA by some R1. And you pass this current through a resistor value R2. If you choose R2 to be larger than R1, then you will get VA times R2 by R. Does it make sense? Okay? Alright. So the question is, how do you generate VA by R1? So in other words, I want to generate an I which is VA by some R1. How do you think I'll be able to do it? Of course, if I have a VCCS, then with the transconductance 1 by R, I'm done, right? But that's hardly an answer, right? I want to figure out a more practical way of doing things than say use an ideal VCCS. How do you realize a VCCS? The things you know are you have op amps. Let's assume you have op amps with you and you have transistors. If you're in the lab and I gave you a variable current source and I wanted you to make the variable current source equal to VI by R, what will you do? If I had a variable current source, right, and I wanted to make this equal to VA by R, VA by R1, what will I do? I will pump this current through a resistor R1, compare this voltage to VA, correct? Okay? And then, if this voltage is, if I call this Vx, if VA is greater than Vx, what does it mean? If VA is greater than Vx, it means Vx is not enough. So I must push Vx up, which means I must increase I. Okay. On the other hand, if VA is smaller than, smaller than Vx, it means that Vx is too high, which means there is too much I must reduce. In other words, this current source must be dependent on the difference between VA and Vx. Okay? Alright? So, what is the simplest variable current source you know? This is now a mechanical current source. You have a knob, you are looking at VA, Vx, going tweaking the knob. Of course, you don't want to, ship a guy along with the bandgap, right? So you want to make sure that all this is done electronically without any knobs of any kind. So what do you want to do? You want an electronically variable current source. What can you think? Can you think of a simple device? What is the simplest variable current source which can push current? Okay. So the simplest variable current source I can think of is a PMOS transistor with this connected to VDD, right? And this is my control knob, right? If I increase the voltage at Vx, at the gate, what will happen to the current? Yes, it will decrease. And if I yank the voltage down, if this is Vg, if I yank Vg down, the current will increase. If I yank Vg up, the current will, if I yank Vg down, the current will increase. If I yank Vg up, the current will decrease. Do you understand or you don't understand? Okay. Now what should I do? I need this current to be controlled by the difference between VA and Vx. Right? So, what should I put there? An op-amp, okay, so that even a minute difference between VA and Vx will administer such a strong kick to the gate such that the current becomes exactly equal to VA by R. Does that make sense? Okay. Alright, and what must be the signs of the op-amp? So, if VA is greater than Vx, then what does it mean? Vx is too low, which means that I is too small, which means that Vg is too high or too low. Vg is too high, so I must bring Vg down. So what should I do? Vx must be negative and this thing must be, which must be positive. If this is too small, Vx must be positive, right? And Va must be negative. And you close the loop like this. Correct? So this is, so if I had a battery Va and so Vx in steady state will be Va, this current will be, Sudhir Prasad, what will it be? Va by R1. Okay. So what will this current be? It will be the same. Okay. Alright. Now if I want to amplify Va, what should I do now? I should take this current and pass it through a larger resistor, right? So, can you suggest something?
Between the transistors.
What can I do to generate a copy of current which is, say, I can put a larger current to the same resistor or the same current to a larger resistor. In other words, I want a copy of this current. What will I do? Current mirror, very good. So this is one way of doing it. Somebody might object and say, why don't you multiply this by some other factor, right? Some k. If this is x, this is kx, right? And this voltage will become k times VA, right? Yeah, you can put a cascode and all that stuff. These are all, they're all lipstick and all that after that, right? But basically, you first have the basic thing working, then you can do all the other stuff, right? So, okay, so you know how to do that. So I will not clutter the diagram. But this is not what we want. What do we want? We want VA minus VB by R1. We want VA minus VB times K. So then it follows that I will want to convert VA minus VB into a current and pass that current into a large resistor. Correct? So if this is VA and this circuit gives me VA by R1, can you suggest something I can? So this current is basically VA by R1, but I want VA minus VB by R1. What do you think I can do? The simplest, yeah. I mean, the cheapest thing you can do is, this circuit gives you VA by R1, right? But you want VA minus VB by R1. So what do? You replace VA with VA minus VB. Seems like straightforward stuff. Okay. So, and how will you generate VA minus VB? If you have two voltage sources, how will you generate VA minus VB? Yes, Venu. You have two batteries, VA and VB, man. How will you generate VA minus VB? I mean, apart from what Sudhir Prasad Komala tells you. Why is the resistor coming? This is VA. I have another battery, VB. If I want to generate VA plus VB, what will I do? I'll put the two batteries in series. If I want to generate VA minus VB, what will I do? Put them in the, so one way of generating VA minus VB, therefore, appears to be the following, which is simply, if this is VA and this is VB, this voltage will be VA minus VB, right? Which means that this will be VA minus VB and this current will be VA minus VB by R1. Does it make sense? Yes? No? Alright. See, please note, I am not trying to pull a fast one, okay? It's all stuff that I would do, if I didn't know anything, this is what I would do, right? And this is precisely the way you must think when you come up with, you're faced with a problem that you have not solved before, right? Okay, so what do you think could be the likely problems with this approach? No, there's no loading here. See, please note what VA and VB are. What are VA and VB? There's VA is basically this, VB is basically this. Okay? Correct? So, current I being passed through one diode, current I being passed through n diodes connected in parallel. So in other words, if I have to realize VA, basically I have to pass some current I through a diode. Correct? So, do you see any problem? It's the problem is immediately obvious, right? VB or VA will always be developed in the direction of current flows from node 1 to node 2, then node 1 will be at a higher potential than node 2. Correct? So while this is a perfectly sane way of finding VA and VB if you are ideal batteries, right? This is definitely not a practical thing from our point of view, simply because for VA there is no problem, because current flows like that, I can simply put a diode instead of VA and I will get the voltage drop I desire. However, for VB, what is the problem? You are expecting the current to flow in the opposite direction, right? Which is therefore not it doesn't work with diodes. Does that make sense? Okay, so that doesn't work. What else can you think of?
So connect the two negative parallel through these two combinations. You can connect the negative terminals and then take the difference across the potential. Connect the negative terminals, then if you take V and put it here, VB at the
okay, so what is being suggested is that this is VB. I'm just going to this is the earlier circuit we had, correct? And we want to make, and I will also draw the directions of currents in various branches. So this is I. This is also, this is the direction of current in this branch is this. Okay? So if I want VA minus VB by R1, but I cannot afford to put VB here because the direction of current is opposite to the direction of in which the voltage is being developed. What can you suggest? Put VB here. Right? Which is basically pushing this VB like this. Okay? So this is VB. Correct? You understand? In other words, one other way of looking at it is you want VA minus VB is equal to I times R. Correct? Which is equivalent to saying that VA must be VB plus IR. So earlier you were just comparing I times R with VA. Now you must compare what? VA with VB plus IR. Okay? And how do you generate VB plus IR? The voltage VB in series with the resistor, and you pump current I into the resistor R. Correct? So this circuit can be arrived at in several ways. Okay? So now the good thing is that
Sir, but how do you ensure the currents are equal?
Wait, 1 second. I will come to that. Okay? So at least now we are better off than before, because in both VA and VB the currents are flowing in a direction, if current is flowing into VB, in such a way that this is compatible with what you would get when you put a diode. Correct? Okay. So let's see. Now what is VB? How will I generate VB? VB is nothing but the N diodes in parallel. Correct? So this is nothing but VB by definition. Correct? Now
That is still VA, right?
Pardon?
The positive node is still VA, right?
Which positive node?
It's op amp terminal.
Yeah, this voltage is still VA. This is VA, this is also VA. I'm sorry, this is not VA minus VB, it is VA. Correct? This is VB. Okay? So VA minus VB by R1 is the current that flows. Everybody is with me on this? Okay. Now what other stuff needs to be done? I need to generate VA. And what is VA? I need to pass current through a diode of size 1, correct? But there is something crucial, and that is, the key point is that I must pass the same current that is flowing in here through this diode. Only then I will get VT ln N. Is that clear? Okay. So I need to pass a current, but this current that I must pass must be equal to VA minus VB by R1. Or if this, I call this, if I call this I, this must also be I. Does it make sense? Okay. Alright, now how will I generate I? The current mirror, right? You understand? No. So, okay, let me discuss that. I think it's very late. So one comment made is that now earlier there was negative feedback around the op amp like this, right? Now it appears as if there is also some positive feedback. For those of you who don't understand why there is positive feedback, I will cover this in the next class. But let me not hold the suspense. Let me quickly generate the bandgap voltage. So this current is what? This current, alright, this transistor is also the same size. So what is this current? VA minus VB by R1, correct? And now I must multiply this up by some K. So if this is KR1, this is also size X. This is VA minus VB times K, correct? And to this I must add VB. So, what is the cheapest thing you can think of? What is VB? You pass current through a diode. So, right? So this is VA minus VB times K plus VB, correct? And this will be equal to VBG. You understand? So you can see that the signs of the op amp and all that come out quite naturally, and this is how the. So at every step of the way, there are several ways of doing, generating this delta VB by R. There are several ways of amplifying it up. Okay. Here we have assumed availability of transistors. If there are no transistors also, you can do it. It's actually quite straightforward. I'll demonstrate that in the next class. Correct. And but you can see that this is what is the basic band gap. Of course, now you've got to make sure with careful circuit design that when the supply voltage changes, bad things don't happen, and so on. As Chinmay was pointing out, you can add lipstick by putting, CAS code, GEAS code, all that stuff, right? And you can improve the performance a little bit, right? I mean, clearly the errors involved in this process are basically, for example, channel length modulation here might make this current not exactly equal to I, right? There might be some error because of finite output impedance and all that. So all this can be fixed by suitable circuit techniques, but this is the basic idea. Okay? Alright.